Hello, everyone. My name is Bryce Harris, and I am the team lead for this project. Our team, consisting of Mike, Gabby, David, Kenny, Garrett, and Zane, worked together over the past few months to develop a software system called CyberCan. CyberCan is a Java-based tool designed to monitor and analyze CAN bus traffic in vehicles. You can think of it like Wireshark, but specifically for cars. We wanted to help developers, technicians, and even manufacturers detect cyber attacks, such as denial of service and message spoofing. Our software will alert the user of unsafe or harmful messages that are not supposed to be in the CAN logs. Our target users include automotive engineers, vehicle security researchers, and developers testing CAN protocols. By providing real-time monitoring and logging of suspicious activity, we can hope CyberCan will minimize potential injuries, insurance costs, and even lawsuits related to cyber vulnerabilities in modern vehicles. In phase one, we sorted out the functional and non-functional requirements for CyberCan. Those features include monitoring CAN traffic, simulating attacks, logging suspicious activity, downloading CAN logs, and injecting messages. We made sure it's expandable, documented, and low cost. We also followed the Scrum process model using Jira for sprint planning, and we used tools like Eclipse, Visual Studio Code, and Busmaster. Now, let's move on to phase two, which focused on requirements analysis. We created a use case diagram in StarUML that outlines the core functionality of CyberCan. We also use Draw.io to make our UML diagrams, but for this specific one, we use StarUML. On the left-hand side of our diagram, we have our actor, the end user. In the center, we have our main use cases. These include simulate attack, capture CAN data, timeout duration, alert suspicious activity, view live CAN traffic, filter live data by ID, log CAN traffic, log suspicious activity, view CAN log, and apply filter. That's about it for this UML diagram. And now that I've introduced you to our project CyberCan, our CAN bus traffic monitoring tool, I've walked you through our goals, our target users, and the core features from the first phase. I'll pass it on over to our next team member who will dive deeper into our development process.
Hello, my name is Garrett Gressley, and I will be covering our domain class diagram and design class diagram. First, I will be showing the domain class diagram. It is a high-level view of the system and concerns the problem space, which in our case is monitoring, analyzing, and logging CAN messages for suspicious activity. We will start with the scan session entity. This is a session during which we are scanning CAN message entities and searching for a suspicious message represented by the suspicious message entity in the diagram. The logger entity creates a list of the CAN messages. The filter, search, and CAN log entities facilitate searching through CAN messages. The timeout setting entity allows the developer to control the amount of time the scan session runs for by setting time limits. The developer entity represents the developer themselves. The log file represents the log of a particular scan session that will be generated, and attack simulation represents an attack created by the developer to determine whether it will be flagged as suspicious by the program. Next, we have the design class diagram. The design class diagram transitions us from a conceptual overview to a concrete implementation of the program. Admin access validates access with a password using the has access method. This enables the ability to write canned messages. The developer selector enables the user to start a scanning session with the scan session class and allows the can message logger class to begin logging can messages. A scan session handles a scanning session. It gets start and end times and determines how long to run a scanning session for. The scan session class uses the can message logger to generate a log of can message objects for the user. Objects of the can message class contain information on the specific can message they represent, such as ID, data, the source node, timestamp, etc. The suspicious can message and suspicious can message filter classes are used for identifying suspicious can message objects. The suspicious can message class detects a suspicious can message object, and the suspicious can message filter class is used to flag and present to the user the detected suspicious can message objects.
Hello, my name is Zane, and I'm going to be doing the second fully dressed cases for our group's project. So, the first one is the set timeout duration. That's the case name. The scope is CyberCAN. The level is user goal, and then the primary actor is developer. So, for the stakeholders and interest, the developer, they're going to be doing the CAN scanning process. Does not run indefinitely, and for the system it needs to automatically stop long scans to avoid poor performance or misuse. Preconditions: the application is running and developer has access to configuration settings. The success guarantee: timeout value is stored and will be enforced during future scans. Scanning operations will be auto stopped after the timeout duration lapses. Main success scenario: so first one, developer opens application settings. Second is developer selects set timeout duration. Third step is system prompts for duration input. Then developer enters a valid timeout. Then system stores the value. And then the very last one is during scanning, if timeout limit is reached, the system stops scanning and notifies the user. For the extensions, invalid timeout value entered. Then it goes to system shows error and prompts for new input. For special requirements, timeout duration should be between 1 and 60 minutes, so 1 minute to like an hour. System will notify user if scan is auto stopped due to timeout. For the technology and data variations list, input can be used like with a text box. The timeout value stored in a config file or database. Frequency of occurrence, frequently during system setup or testing, and then miscellaneous. Future updates might include different timeout profiles per user or scan type. And then the second one is log suspicious activity. The scope is of course CyberCAN. The level is user goal. Primary actor CyberCAN. So the developer, for stakeholders and interest, developer wants to detect the abnormal CAN traffic, and then vehicle owner concerned with system security and attacks. The preconditions: the CAN scan is active, system is connected to the CAN bus and has access to message patterns. The success guarantee: suspicious message is recorded in the database, notification is generated. Main success scenario: so system monitors live CAN traffic. Second is system detects a message pattern that does not match known/abnormal behavior. Third one is system flags this message as suspicious. Fourth is system logs the message with timestamps, ID, and context to the database. Fifth is system displays or logs a notification indicating a suspicious message was detected. Extensions is no database connection, then log is stored locally until a connection is available. if the log fails, then retry or mark as temporary. Special requirements: logging must occur with low delay. Notification can't interrupt scanning. Technology and data variations list. Logging mechanism could use SQL-based databases, so like MySQL, SQLite. Detection algorithm based on patterns. Frequency of occurrence, occasionally based on potential attack activity. And then some of the miscellaneous stuff is may categorize severity levels or add alerting with tools like email or like a text. And then the next one is stimulate attack. So same thing, scope, cybercan, level is user goal, and then the primary actor end user. Um, Stakeholders and interest, car producers, so they want to test their CAN bus against a potential cyber attack, wants to minimize lawsuits, insurance costs, warranty costs, and etc. And then for the owners, want protection against injury due to cyber attacks, so want to save money by preventing the theft of their property. Preconditions: the application is running and CAN bus is connected. A cyber attack on the CAN bus has been simulated. Data related to the simulation has been saved. That's for the success guarantee. For the main success scenario, so the first step would be user has an existing CAN bus connection to run a simulation on. User is prompted to simulate a weeping CAN attack or a CAN frame attack. Third one is user initiates a weeping CAN attack. Fourth is system performs weeping CAN attack on the user's CAN bus. Fifth is system reports back information regarding the attack. And then sixth is system saves a log of information to the database. For the extensions, no CAN bus detected. For like the first step, stops the use case early if hardware isn't ready, prevents unnecessary errors. And then for the next one, which is like 6A, database connection fails, then that ensures logs are lost, critical for traceability and debugging. There's no special requirements on there. And then the technology and data variations list, busmaster simulation, software to simulate CAN buses, and then frequency of occurrence could be used multiple times in a day. And then there's nothing extra, miscellaneous or anything like that. So next one is download logs. Scope, cybercan, level is user goal, and then the end user, is our primary actor. End user wants to easily download attack simulation logs from the database in a legible format. Wants a reasonable file size and a file type that is widely used and therefore accessible. For the preconditions, an attack has been simulated and subsequently generated log of the report has been saved. For the success guarantee, user has downloaded a log of their choice. The main success scenario, user accesses list of logs through cybercan UI, and then the user selects logs that they wish to download. Then they access the chosen logs and download them to their own computer. There's no extensions and there's no special requirements for that. The technology would just be SQL-based databases, so like MySQL, SQLite. And then the frequency of occurrence could occur multiple times a day, and many files may be downloaded at one time. And there's no extra miscellaneous stuff on there. Last one is the start capture. So scope is cybercan, level is user goal, primary actor is cybercan. For the stakeholders and interest, technicians and manufacturers would like to get the most accurate real-time results. So for the preconditions, CAN needs to be connected to something that allows the test and has necessary software installed. For the success guarantee, allows live data to be recorded and processed. And then the main success scenario, first CAN is turned on and test environment works, start capture, then the tool will start grabbing data and analyzing. For some of the extensions, or one of the extensions, the test environment does not work, and many errors will show. Special requirements is UI to display messages for users to see data. For the technology and data variations list, CAN data, test environment, and a UI for like all the devices. For the frequency of occurrence, during testing and developing, miscellaneous can be integrated with different code readers. And that would be it for the second fully cased cases.
I'll be Hosai, and I'll be going over the 5 fully dressed use cases. The first one is search by ID. The scope is CyberCAN. The level is user goal. Primary actor is CyberCAN. The stakeholders and interests are the technicians and manufacturers, so that they can easily go in and put in the ID that they're looking for, and the data will come out. Preconditions are that the CAN is connecting and working, and it is able to grab data by their IDs. The post conditions are that allows data to be searchable and shows information from specific IDs, so when someone wants to go in, they put in the ID and data comes out. The main success scenario is first, CAN is turned on and it works, starts to capture, it grabs the data, and then a person can go in, put in the ID, and grab the data that they need. Extensions is that the filter doesn't work or it doesn't show anything when you put in the ID. Special requirements are that you could add security and combine numbers and letters. The technical and data variations list, CAN live data, test environment, CAN IDs. Frequency or occurrence is during testing and developing. Miscellaneous is you can add different filters and make things downloadable. The next one is alert suspicious activity. This is also used by CAN. The level is user goal. Primary actor is CAN. Stakeholders and interests are the developers and system users, so that they can be notified immediately when there's something abnormal. Preconditions is that the CAN is working. CAN, it scans and monitors live traffic. The post conditions is that alert is generated and shown in red text in the log with pop-up. The main success scenario is the CyberCAN monitors incoming traffic. A message matches known suspicious problem. The message is flagged and it pops up on the screen. Extensions is that there is no alert and nothing pops up. So special requirements are that alerts do not interrupt scanning, and pop-ups should be dismissible. The frequency is occasionally when suspicious activity is detected, and miscellaneous is that the pop-ups can be auto-dismissed in the future. The next one is view CAN traffic. Scope is the CyberCAN, level is user goal. Primary actors are the developers, technicians, and the users. Stakeholders and interests are that the users want to view real-time CAN traffic to analyze errors and things like that. Preconditions is that the system is running and can grab data from the CAN. The post conditions are that the CAN traffic is displayed in the interface, including ID, timestamp, source, and content. Main success scenario is that first the user opens the CAN traffic, the system starts displaying CAN messages. Each system shows what needs to be shown. Users observes the messages live or from stored logs. Extensions is that no live CAN data shows, and it shows an NA. Special requirements is that your display must update in real time without freezing and is scrollable. And frequency is frequently during testing and things like that. Miscellaneous is filters and searches are part of separate use cases. The next one is load CAN log. CyberCAN is the scope, user goal is the level, CyberCAN is the primary actor. Stakeholders and interests are developers. They want to be able to analyze this CAN traffic. Preconditions is the system is running and accessible. CAN log exists and is stored, and users can necessarily have permission to access the CAN logs. The post conditions is that CAN log data is successfully loaded into the system and is available for analysis. The success scenario is developer selects load CAN log, system prompts file selection, developer selects file, system verifies file, and then it shows the file that is uploaded. Extensions: no CAN log available and it doesn't work, invalid file, and loads wrong file. Special requirements: log loading should not significantly delay the responsiveness. Technology and data variations list is CAN log stored in storage log formats, system compatible with databases like MySQL. Frequency of occurrence is on demand basis whenever someone needs it. Miscellaneous is consider future integration with automatic detection or analysis tools. The last one is apply filter. This is also used by CAN. It is user goal level. Its primary actor is CAN, and the stakeholder and interests are developer. The developer wants to narrow down CAN log data to isolate specific events. The preconditions are that the CAN log data has successfully loaded into the system and is able to filter. Success guarantee, the postconditions, is the filter results are displayed clearly and accurately. The success scenario is developer selects the apply filter option. System presents available filtering criteria. Developer sets the desired criteria. System applies the filter and system shows the log data. Extensions is invalid or incomplete criteria. Filter application fails due to system issues. Special requirements are that filter application should be rapid and usability. Technology and data variation lists support filters based on timestamps, IDs, things like that, compatible with MySQL. Frequency of occurrence is frequently whenever needed. Miscellaneous is future improvements may include advanced filters.
Hi everyone, my name is Kenny Hartwell and I'm going to be discussing the design sequence diagrams for Team 3. Our first sequence diagram is displaying logs. So in this interaction, the end user will initiate the process by opening the log list via the log UI. From there, the log UI delegates the request to the log manager, which queries a database. Once the log list is retrieved, it's returned back up the chain to be displayed to the user. This sequence ensures the system provides up-to-date logs seamlessly, showing a clear separation between user interface, logic, and data access layers. Our second sequence diagram is the download logs. This sequence outlines how a user downloads specific logs. The end user selects logs using the log UI, triggering a download request. So the file exporter will handle this request by contacting the log manager, which fetches the logs from the database. Once retrieved, the logs are passed back to the file exporter, which packages them into a downloadable zip file and initiates the file transfer. It's a clean pipeline ensuring selected logs are securely and efficiently delivered to the user. Our third sequence diagram, log suspicious activity, is where we focus on real-time threat detection. The CAN monitor captures the message and forwards it to the activity monitor, which analyzes it for suspicious behavior. If suspicious behavior is detected, it will flag said behavior and it will log the event using the logger and notifies the notification monitor to alert the user. This quick response chain ensures both awareness and traceability of abnormal activity, critical for a secure CAN system. Now over here we have our simulate attack design sequence diagram. So this slide demonstrates how a user simulates an attack for testing. The end user selects an attack type via the attack UI, initiating a series of calls through the attack manager to the bus interface, which executes the attack. The result is returned and logged for later review. This simulation capability is vital for proactive testing and hardening of CAN network defenses. Over here in our fifth sequence diagram, start capture is used for beginning a message capture. The system initiates this via the capture controller, which starts reading from the CAN interface in a continuous loop. Messages are passed to the analyzer, which decodes them and forwards the results to the display manager. The output is then rendered to the user, allowing live CAN traffic monitoring with decoded insights. In our sixth design sequence diagram, we have the timeout duration. Now this interaction helps developers configure timeouts. The developer will begin by entering data into a UI text box. After that, the timeout validator confirms input validity and, if correct, sends the duration to the configuration manager to be stored. This gives the system flexibility to accommodate different timing requirements during development and deployment. Over here we have the search by ID sequence diagram. In this special case, the end user searches for a CAN message by its own message ID. The search UI processes the input and queries the CAN log manager, which interacts with the logger to retrieve matching entries with those that are being inputted. These results are returned and then shown to the user. Now, this flow helps in diagnosing issues or tracking down specific events quickly and intuitively with just a simple search. Our eighth sequence diagram is alert suspicious activity. So here's the flow when a user manually flags a suspicious event that is completely separate from when the system does it by itself. Pressing the alert button triggers a alert request through the alert UI to the activity monitor. The notification monitor then displays the alert. It's a user-driven complement to automated detection and allows manual intervention when needed. Our ninth sequence diagram is view CAN traffic. This sequence begins when the end user opens the CAN traffic page. The traffic UI gets the data from the CAN monitor and applies user-specified filters. The filtered results allow targeted inspection of the traffic, an essential tool for debugging and forensic review. Over here we have the load CAN log diagram. Here the user loads a previously saved log. After the end user selects a file, the log UI initiates parsing via the log manager and logger. The parsed data is returned and presented. This feature is crucial for replaying scenarios or reviewing historical traffic offline.
Hello, welcome to the CyberCAN project. My name is David Hudson, and I was co-software developer along with Mike, and I helped come up with the idea for CyberCAN. As currently I work for an automotive OEM, so I deal with CAN at my job basically all the time. So let's go ahead and get started. So with CyberCAN, I guess the question I'm going to start with is, can your car really get hacked? Yes, maybe some of you have heard of, especially lately with people being able to hack cars and steal them, stuff like that. But yes, your vehicle can get hacked, and this has been going on for years, quite some time. But what's kind of changed maybe in about the last 10 years is now that we have wireless transmitters that we're using to start our cars rather than the physical keys. Which I think most automotive OEMs have gotten rid of the keys, as far as I know. But with the addition of these wireless transmitters, it allows hackers to not actually have to physically connect wires to your vehicle, so they can do this somewhat wirelessly. And with manufacturers starting to go the way of implementing OTA, or over-the-air vehicle updates, which uses cell towers and satellites to connect to those vehicles and send the updates. Hackers now can get hack these vehicles from their PC, and as like I said, somebody who's currently working for an OEM, that's why I'm starting to see IT be involved a lot more with daily operations, because we need them for security with these over the air updates. So with that said, I'd like to go and transfer to the next question: what is CAN? So our CyberCAN project uses CAN, and CAN was developed in 1986 by the Robert Bosch Company, and it is a serial communication, and the original intent was to provide a vehicle or a vehicle's ECUs with some type of network, so that these ECUs could talk
to each other. Um, Many of these ECUs are going to be used for controlling the engine, um, could be ABS system, airbags, seats, HVAC, all types of things in your vehicle. But CAN's also has become so popular, even after its original intention for a vehicle. You now can see it in other applications, such as like industrial applications. Many sensors and stuff in the industrial world use CAN. So why are the automotive manufacturers, mainly automotive manufacturers, using CAN? Well, for the automotive manufacturers, the bus is simple. It uses two wires, which are CAN low and CAN high, as you can see in this picture. And with only using two wires, it reduces the amount of wiring needed in the vehicle, and it lowers its weight. Also, the two wires makes it very simple for removing or adding more nodes in the CAN bus. Most CAN buses allows for up to 255 different nodes. The automotive world tends to keep that lower than, say, 100 devices on a single CAN network. Another reason why they use CAN, the CAN chips are cheaper than most other serial chips out there, such as like an Ethernet chip or Modbus chip. And then the last reason why they're using CAN is it's fast and efficient, and it's crucial for the real-time data that the automotive industry needs. For example, you get into an accident, you need that real-time high-speed data so that your whether it's your airbag module or body control module that deals with the safety systems that's looking at, say, crash sensors, can tell the other ECUs that, hey, we've been in an accident, get into your shutdown mode, whether it's shutting down the engine, that type of stuff in the vehicle. The CAN message itself, I'm not going to go too much into it, but from a high level, when I teach other people at my work how CAN works, the two big things to worry about is the ID. Every single CAN message has a unique ID. It's important because all the other nodes on the CAN bus will see that unique ID, and they have to determine themselves if that data is meant for them or not. And then the other part of the standard message is part of the message is the standard CAN frame that holds the data. Standard CAN can, I think, has up to 8 bytes. They've now introduced what's called CAN FD, which will allow up to 64 bytes. That was recently introduced about 2015 because of the need in these vehicles for more data transfer for things such as the cameras in the vehicle and some of the self-driving devices that they've added to the vehicle. But with that said, CAN kind of poses a somewhat a security threat because, like I said, the data right here, it's not encrypted or anything. It's just an ID and in data. So if somebody reverse engineers that stuff, they can start figuring out what these messages mean and figure a way how to hack the vehicle. The last thing I'm going to talk about is our CyberCAN API. So we are using the PCAN API from a company called Grid Connect, which I'm very familiar with. I've never used this API until this project, but I have a USB PEEK adapter here. or as shown, and I hook that up to my laptop, and that allows me to communicate from the PC to the CAN bus um, over USB. So as you can see in this picture, I have a Windows, showing my Windows PC. I've got my CyberCam application. Inside of it, I got my CyberCam API and shown that it's connected to USB. And from there, the USB is connected to the CAN device, which connects to the CAN bus. Which also pretty neat is the API also includes languages such as Python, C++, C Sharp, and VB. Thank you.
Hi everyone, I'm Mike, and this is our final demo of the CyberCAN app. It's a Java-based security application that simulates and monitors a real-time CAN bus system, just like the one you would find in a modern vehicle. It allows developers to run scan sessions and view live CAN messages, while admins can unlock more advanced features like sending test or malicious messages to the bus. We built this using the MVC design pattern, and this helped keep the logic modular, testable, and maintainable. So now that we went over the introduction, let's see how we would begin using this and go over some of the features. So here in the center of the screen, you can see the graphic user interface here, and it's labeled CAN Message Simulator, CyberCAN. So to begin, what we would do is select a developer to allow scanning to happen. So right now, prior to selecting a developer, you can't start a scan session. You'll also see that the timeout is at 60 seconds. We incorporated this to not overload the system. So you can adjust that, and we'll go over that feature later. But for now, let's begin with selecting a developer. So once we select that, we'll see we are given a prompt here or a message in our CAN log message area. This is kind of one of the focal points for the outputs, and a lot of the features that we click or do will be reported back in the same window. So now that we have a developer selected, we can start a scan session. The timeout section here is going to be 60 seconds. There's a running timer here. We can adjust this, and we'll trigger this later. But for now, let's just start. And we can see the messages starting to roll in. Something you may notice, you have an ID here, data, the 8-bit piece of data. The node is basically just a subsystem of the vehicle, and then a timestamp. So we're going to go ahead and stop this. We're going to go ahead and clear the log. You can see that it's been updated to let us know that we had cleared the log. So in order to write your own messages or simulate an attack, you would have to first then put the password into the fields here. And just like modern password fields, you can kind of toggle that and see if it's right or not. So now that we have that put in, you can see that this button, we can actually interact with this button. So we'll go ahead and start this again. And you can see the automated generated messages coming in. And we'll do our own. If we just hammer this here, you can see that we're able to write to the window too. So having done that, we know that we can inject messages right into the CAN message log. So if we wanted to simulate a malicious attack from somebody outside the system, trying to either hack or just get into the system to do something you don't want, we would look at the suspicious filter flagged IDs section here. So now that we have admin rights, we can go ahead and change the makeup of a message. So if I wanted to trigger that, I would just enter something from our list down here, and then I would write that. So if I hit that several times, you can see that we are indeed picking up that this is a suspicious message, and it has some of the same signatures as a normal message, but it'll say blocked ID, severity high, etc. Okay, so now we see that we also allowed the timeout to take effect. So it ran for over 60 seconds, and at that time, it'll let you know that your session has ended, and it has a start and end date too. And then it gives you just like a quick sanity check of why it stopped, timeout true. So there's that for you there as well. So let's say you wanted to update the list here. So it's just a comma separated value list. So if you wanted to do this and say just something like type that in, and then you update that, now you'll be prompted that your flagged IDs has changed. So to prove that out, we'll go ahead and change that to that. We'll start the logger up again, and we'll see that because the ID is something that's in the suspicious filter flagged ID list, that it will be received as malicious. Okay, so we can also shorten this, and we'll just see that you can set this from 1 second to, upwards over a minute, so on and so forth. Okay, so that has taken effect here. All right, so just like before. All right, next, there's a suspicious only message. So if you check this box and you start a session, and if you just do malicious attacks, it'll show that. But if you enter something that isn't on this, then it won't show that. But if we do that again, and that'll prove that out as well. Okay, so those are some of the features that we have. One of the last ones here is save to log. So what this is going to do is this is going to allow you to write this to a text file, and then we can retrieve that. So I'll go ahead and do that, and you have a prompt here confirming that. And that text message is, the text file is going to be sent just to wherever your project is located. So when you open that, you'll see just basically a collection of messages that was in the CAN log message area. So I guess a couple of things that we probably could have included that moving forward to improve on it is like a suspicious counter, just kind of increment the amount of suspicious CAN message IDs that are blocked and considered a threat. Another one would be transferring the text file to like a database, like Maria database using XAMPP or something similar to that. Yeah, so that's the project. Thanks for watching, and I wanted to thank everybody on the team for all the hard work throughout the semester. Thank you.